Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast emptiness between stars, where temperatures plunge to just a few degrees above absolute zero, ancient travelers drift through the cosmic void. These are the rogue comets, solitary wanderers that have broken free from the gravitational embrace of their parent stars and now journey alone through interstellar space. Unlike the familiar comets that grace our night sky with predictable returns, rogue comets follow no orbital pattern. They are cosmic nomads, carrying within their frozen cores the chemical signatures of distant stellar systems. When astronomers first began detecting these objects in the early 2000s, they realized they had stumbled upon something extraordinary. Messengers from other worlds, bearing secrets about the formation and evolution of planetary systems across the galaxy. The discovery of rogue comets challenged fundamental assumptions about how comets behave. Traditional comets, like the famous Halley's Comet, are gravitationally bound to their host stars. They follow elliptical orbits, swinging close to their star before retreating to the cold outer reaches of their solar system. But rogue comets have escaped this cycle entirely. They represent a population of objects that astronomers estimate could number in the trillions throughout our galaxy alone. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. The physics behind rogue comet formation involves a delicate interplay of gravitational forces. Most begin their existence as ordinary comets within planetary systems. However, gravitational interactions with massive planets can sometimes accelerate. These icy bodies beyond their systems escape velocity. Once they reach speeds exceeding 11.2 kilometers per second, relative to their host star, they break free and begin their solitary journey through space. Scientists classify rogue comets into two primary categories based on their origins. The first group consists of objects ejected from our own solar system, comets that experienced close encounters with Jupiter or Saturn and were subsequently flung into interstellar space. The second, far more intriguing category includes comets that originated in distant stellar systems and have traveled for millions of years before entering our cosmic neighborhood. The challenge of detecting rogue comets lies in their extraordinary faintness and unpredictable trajectories. Unlike bound comets that develop distinctive tails when heated by their star, rogue comets remain dormant during most of their journey. They appear as nothing more than faint, moving dots against the star-filled background, making them incredibly difficult to spot, even with advanced telescopes. Recent surveys conducted by the Catalina Sky Survey and the Lincoln Near-Earth Asteroid Research Program have revolutionized our understanding of these objects. By analyzing the orbital characteristics of newly discovered comets, astronomers can determine which ones are merely visiting our solar system versus those that call it home. The visitors, the true rogue comets, display hyperbolic trajectories that clearly indicate their interstellar origins. The implications of rogue comet research extend far beyond simple astronomical curiosity. These objects serve as natural laboratories for studying the conditions present in other stellar systems. Their chemical composition, preserved in pristine condition by the cold of interstellar space, provides direct evidence about the materials that formed planets around distant stars. Some scientists speculate that rogue comets might even transport organic compounds between stellar systems, potentially playing a role in distributing the building blocks of life throughout the galaxy. As we prepare to delve deeper into the science of these cosmic wanderers, we find ourselves at the threshold of a new era in astronomy, one where the boundaries between our solar system and the broader galaxy become increasingly blurred. Detecting rogue comets represents one of astronomy's most formidable challenges. These objects, typically measuring just a few kilometers across, hurtle through space at velocities reaching 30 kilometers per second, while remaining virtually invisible to most observational techniques. The task resembles searching for a grain of sand, flying through a darkened stadium while wearing sunglasses. The breakthrough in rogue comet detection came through automated sky surveys designed originally to identify potentially hazardous asteroids. The Catalina Sky Survey, operating from the Catalina Mountains in Arizona, uses a 1.5-meter telescope equipped with highly sensitive CCD cameras to photograph the same patches of sky multiple times each night. By comparing these images, computers can identify objects that move against the background stars. The Lincoln Near-Earth Asteroid Research Program, known as LINEA, employs a similar approach but with even greater sensitivity. Using a 1-meter telescope at the Lincoln Laboratory Test Site in New Mexico, LINEA has discovered over 200,000 asteroids and comets since 1998. The program's sophisticated software can detect objects as faint as 19th magnitude, roughly 400,000 times fainter than the dimmest star visible to the naked eye. Distinguishing rogue comets from ordinary asteroids requires careful analysis of their orbital characteristics. When astronomers plot an object's trajectory, they calculate its orbital eccentricity, a measure of how elongated its path appears. Regular comets and asteroids bound to our solar system display eccentricities less than 1. However, rogue comets exhibit hyperbolic orbits with eccentricities greater than 1, indicating they possess sufficient velocity to escape the Sun's gravitational influence. The spectroscopic analysis of rogue comets provides additional confirmation of their nature. When these objects approach the Sun closely enough to begin sublimating, they release gas and dust that can be analyzed using specialized instruments. The Hubble Space Telescope and ground-based observatories equipped with high-resolution spectrographs can detect the characteristic emission lines of water vapor, carbon monoxide, and other volatile compounds that distinguish comets from rocky asteroids. One of the most significant challenges involves the timing of observations. Rogue comets typically become detectable only when they venture within the inner solar system, where increased solar heating begins to activate their volatile components. This window of opportunity may last just a few months before the object retreats beyond the reach of current telescopes. Missing this opportunity means losing the chance to study that particular rogue comet for potentially millions of years. The upcoming Vera Rubin Observatory in Chile promises to revolutionize rogue comet detection. This facility, featuring an 8.4-meter primary mirror and the world's largest digital camera, will conduct the legacy survey of space and time. Beginning in 2025, this 10-year project will photograph the entire visible sky every few nights, creating an unprecedented database of moving objects. Advanced computational techniques now assist astronomers in processing the enormous volumes of data generated by sky surveys. Machine learning algorithms trained to recognize the subtle signatures of rogue comets can analyze thousands of images simultaneously, identifying potential candidates for human review. These systems have already proven capable of detecting objects that human observers might overlook. The European Space Agency's Gaia mission, while primarily designed to measure stellar positions and motions, has serendipitously discovered several rogue comet candidates. Gaia's exceptional precision allows it to detect the tiny positional changes that indicate an object's motion through space, even for extremely faint targets. Recent technological advances in adaptive optics and infrared astronomy have opened new windows for rogue comet research. Ground-based telescopes equipped with adaptive optic systems can now achieve image quality rivaling space-based observatories, while infrared instruments can detect the thermal emission from these cold objects even when they're not actively sublimating. The next frontier in rogue comet detection involves space-based surveys specifically designed to identify interstellar objects. Proposed missions like the Near-Earth Object Surveyor would operate from locations beyond Earth's atmosphere, providing continuous monitoring capabilities free from weather-related interruptions and atmospheric interference. The first confirmed interstellar visitor to our solar system arrived unannounced on October 19, 2017. Initially catalogued as Asteroid 2017 U1, this object would soon challenge everything astronomers thought they knew about interstellar wanderers. Within days of its discovery by the Panoramic Survey Telescope and Rapid Response System 1 telescope in Hawaii, scientists realized they were observing something extraordinary. The first definitively identified rogue object from beyond our Solar System. The object received the name Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. Measuring approximately 400 meters long and 40 meters wide, Oumuamua displayed a highly elongated shape, unlike any comet or asteroid previously observed in our solar system. Its unusual proportions, roughly 10 to 1 length to width, ratio, suggested it might be a fragment of a larger body shattered by gravitational forces during its long journey through space. Oumuamua's behavior proved even more puzzling than its appearance. As it rounded the Sun, the object exhibited a slight but measurable acceleration that couldn't be explained by gravitational forces alone. This non-gravitational acceleration, first detected by the European Space Agency's Gaia mission and confirmed by ground-based observations, suggested Oumuamua was outgassing like a comet. However, no visible coma or tail accompanied this acceleration, leading to intense scientific debate about the object's true nature. The discovery of Oumuamua triggered an unprecedented international observational campaign. Telescopes around the world, from the Atacama Large Millimeter Array in Chile to the Green Bank Radio Telescope in West Virginia, focused their attention on this cosmic visitor. The Breakthrough Listen project even searched for artificial signals from Oumuamua, though none were detected. Spectroscopic observations revealed that Oumuamua's surface appeared reddish in color, similar to objects found in the outer regions of our solar system. This coloration likely resulted from cosmic ray bombardment over millions of years, gradually altering organic compounds on the object's surface. The lack of detectable water vapor or other typical comet emissions suggested either a composition different from solar system comets or a surface layer that prevented volatile materials from escaping. Just 2 years later, on August 30th, 2019, amateur astronomer Gennady Borisov discovered another interstellar visitor using a 65-centimeter telescope he had built himself. This object, designated 2I/Borisov, displayed characteristics more consistent with traditional comets. Unlike Oumuamua, Borisov developed a distinct coma and tail as it approached the Sun, confirming its cometary nature. Borisov's arrival provided astronomers with a more extended observation window. While Oumuamua had already passed its closest approach to the Sun when discovered, Borisov was detected while still approaching, allowing for months of detailed study. International collaboration reached new heights as observatories coordinated their efforts to maximize scientific return from this rare opportunity. The Hubble Space Telescope captured stunning images of Borisov's nucleus fragmenting as it rounded the Sun. These observations revealed that the comet consisted of loosely bound material held together by weak gravitational forces, exactly what scientists expected for a pristine object from the outer regions of another stellar system. The fragmentation also provided opportunities to study the comet's interior composition, normally hidden beneath protective surface layers. Chemical analysis of Borisov's coma revealed water vapor, carbon monoxide, and other compounds typical of solar system comets. However, the ratios of these materials differed significantly from what astronomers observe in local comets. The carbon monoxide to water ratio in Borisov's coma was roughly 50 times higher than typical solar system values, suggesting formation in a much colder environment than our outer solar system. The study of both Oumuamua and Borisov highlighted the critical importance of rapid response capabilities in astronomy. These objects spend only months within range of detailed observation before disappearing into the darkness of interstellar space. Future discoveries will require even faster identification and characterization to maximize scientific opportunities. Both objects provided invaluable insights into the formation and evolution of planetary systems beyond our own. Their chemical compositions, physical characteristics, and orbital properties serve as fossil records of conditions present in their birth environments billions of years ago. Scientists estimate that objects like Oumuamua and Borisov pass through the inner solar system several times per year, though most remain undetected due to their small size and rapid motion. The discoveries of these interstellar messengers marked the beginning of a new era in comparative planetary science, where we can directly study materials from other stellar systems without leaving our own cosmic neighborhood. The birth of a rogue comet begins in the turbulent early stages of planetary system formation, when gravity and chaos dance together in a delicate cosmic ballet. 4.5 billion years ago, our own solar system experienced this same violent choreography, ejecting countless comets into the interstellar void while shaping the orbital architecture we observe today. Computer simulations reveal that planetary systems naturally produce rogue comets through a process called gravitational scattering. When a comet ventures too close to a massive planet like Jupiter, the gravitational interaction can dramatically alter its trajectory. Most encounters result in the comet being deflected into a different orbit, but approximately 1 in every 1,000 interactions provides enough energy to exceed the system's escape velocity entirely. Jupiter, with its massive gravitational field, acts as both protector and destroyer in our solar system. While it shields inner planets from many potentially hazardous comets by deflecting them outward, it also serves as the primary mechanism for creating rogue comets. Scientists estimate that Jupiter has ejected roughly 1 Earth mass worth of cometary material since the solar system's formation, a staggering quantity representing billions of individual objects now wandering the galaxy. The process of comet ejection follows well-understood principles of celestial mechanics. When a comet approaches a massive planet, it gains kinetic energy at the expense of the planet's orbital energy. Although this energy transfer is minuscule compared to the planet's total orbital energy, it can be sufficient to accelerate the comet beyond the system's gravitational binding. The comet then begins its journey into interstellar space, carrying with it the chemical fingerprints of its birth environment. Recent theoretical work suggests that the efficiency of comet ejection varies dramatically between different types of planetary systems. Systems with massive planets located close to their host stars, known as hot Jupiters, may eject comets at rates thousands of times higher than systems like our own. This enhanced ejection occurs because hot Jupiters likely migrated inward from their formation locations, gravitationally disrupting entire populations of comets during their journey. The NICE model, developed by astronomers in Nice, France, provides a comprehensive framework for understanding early solar system dynamics. This model proposes that the giant planets underwent a period of orbital instability approximately 600 million years after the solar system's formation. During this chaotic epoch, Jupiter and Saturn crossed a 2-to-1 orbital resonance, triggering massive restructuring of the outer solar system and ejecting vast numbers of comets into interstellar space. Chemical analysis of interstellar comets provides direct evidence about conditions in other planetary systems. The high carbon monoxide to water ratio observed in comet Borisov suggests formation in an environment colder than our solar system's comet-forming regions. This chemical signature implies that Borisov originated in the outer reaches of its parent system, where temperatures remained low enough to preserve carbon monoxide ice over billions of years. Statistical analysis of known interstellar objects suggests that every cubic astronomical unit of space contains approximately 1 rogue comet larger than 100 meters in diameter. This population density implies that our galaxy hosts roughly 10 to the power of 26 rogue comets, a number so vast that it challenges comprehension. These objects represent a significant reservoir of water and organic compounds distributed throughout interstellar space. The age distribution of rogue comets reflects the history of planetary system formation in our galaxy. Older comets, ejected when the galaxy was young and star formation rates were higher, dominate the population. However, younger systems continue to contribute new rogue comets at a steady rate, maintaining this vast interstellar population over cosmic time. Recent discoveries suggest that some rogue comets may originate from stellar encounters rather than planetary interactions. When 2 stars pass close to each other, their gravitational fields can disrupt the outer regions of each other's comet clouds, launching objects into interstellar space. These stellar encounters occur regularly in the dense stellar environments found in globular clusters and the galactic center. The study of rogue comet dynamics has revealed unexpected connections between planetary system architecture and interstellar populations. Systems with multiple giant planets in eccentric orbits prove particularly efficient at producing rogue comets, as these configurations create complex gravitational interactions that frequently result in comet ejection. Conversely, systems with planets in nearly circular orbits like our own eject comets at relatively modest rates. Understanding rogue comet origins provides crucial insights into the broader processes of planetary system evolution and the distribution of volatiles throughout the galaxy. The future of rogue comet research stands poised at the threshold of revolutionary discoveries that could fundamentally alter our understanding of life's distribution throughout the cosmos. As technology advances and our observational capabilities expand, these interstellar wanderers are transforming from curious astronomical oddities into potential keys for unlocking the mysteries of astrobiology and planetary formation across the galaxy. The Vera Rubin Observatory, scheduled to begin operations in 2025, will inaugurate a new era of rogue comet detection. This facility's unprecedented survey speed will enable the discovery of dozens of interstellar objects annually, providing statisticians with the large sample sizes necessary to understand the true population characteristics of rogue comets. Early estimates suggest the observatory will detect between 1 and 10 interstellar objects per month, creating a steady stream of targets for detailed study. Future space missions specifically designed to intercept and study rogue comets are already under development. The European Space Agency's proposed Comet Interceptor mission, scheduled for launch in 2029, will position itself at the L2 Lagrange point, awaiting the discovery of a suitable long-period comet or interstellar visitor. Once a target is identified, the spacecraft will deploy multiple probes to study the object from different angles simultaneously, providing unprecedented three-dimensional mapping of an interstellar comet's structure and composition. NASA's concept for an interstellar probe mission envisions a spacecraft capable of reaching velocities exceeding 20 kilometers per second, potentially allowing it to catch up with previously discovered interstellar objects after they leave our solar system. Such a mission would provide extended observation periods impossible with ground-based telescopes, enabling detailed study of how these objects behave in the cold depths of interstellar space. The development of next-generation telescopes promises to revolutionize our ability to characterize rogue comets. The James Webb Space Telescope has already demonstrated its capability to detect water vapor and other volatiles in distant comets. Future instruments with even greater sensitivity will enable detailed chemical analysis of interstellar objects, potentially identifying complex organic compounds that could provide insights into the prevalence of life's building blocks throughout the galaxy. Advanced propulsion technologies under development could enable rapid response missions to newly discovered interstellar objects. Solar sails, ion drives, and even theoretical fusion rockets could provide the high-velocity capabilities necessary to intercept these fast-moving targets before they disappear into the outer solar system. The window of opportunity for studying. Each rogue comet typically lasts only months, making rapid response capabilities essential for maximizing scientific return. Sample return missions represent the ultimate goal of rogue comet research. Bringing pristine material from another stellar system back to Earth would enable laboratory analysis impossible with remote sensing alone. Such samples could contain preserved organic compounds, isotopic signatures indicating their formation, environment, and possibly even biosignatures if life exists elsewhere in the galaxy. The technical challenges are immense, but the scientific payoff could be revolutionary. The astrobiology implications of rogue comet research extend far beyond simple chemical analysis. If these objects transport organic compounds between stellar systems, they could serve as vectors for distributing life's building blocks throughout the galaxy. The panspermia hypothesis suggests that life itself might spread between worlds via comets and asteroids, making rogue comets potential carriers of biological material across interstellar distances. Recent laboratory experiments have demonstrated that complex organic molecules can survive the harsh conditions of interstellar space for millions of years. Amino acids, nucleotide bases, and other biologically relevant compounds remain stable when protected within the icy matrices typical of comet nuclei. This preservation capability suggests that rogue comets could indeed serve as natural laboratories for studying prebiotic chemistry under conditions impossible to replicate on Earth. Machine learning and artificial intelligence are transforming how astronomers identify and track rogue comets. Neural networks trained on vast databases of astronomical images can now detect potential interstellar objects with accuracy exceeding human observers. These systems continuously monitor sky survey data, providing real-time alerts when promising candidates appear. The establishment of an international rogue comet response network would coordinate observations and maximize scientific return from future discoveries. Such a network would include rapid communication protocols, standardized observation procedures, and shared data repositories accessible to researchers worldwide. The brief observation windows available for each interstellar visitor make international cooperation essential for comprehensive study. As we stand on the brink of this new era in astronomy, rogue comets offer unique opportunities to study the broader galaxy from our own cosmic doorstep. These ancient messengers carry within their frozen hearts the secrets of distant worlds, potentially providing our first direct evidence of conditions in other stellar systems and the distribution of life throughout the cosmos. The next decade promises discoveries that will reshape our understanding of our place in the universe.